GI physiology, bile, and bilirubin. All right, so you might be asking me why would I be kind of lumping bile and bilirubin together? I'm going to make this all very, very, very clear to you at the end of this video, okay? But let me just kind of walk you through what's going on first and foremost. So let's start with bile. So bile is just bile salts, okay? And it's just made up of like these hydrophilic conjugated bile acids. They're known as glycine and taurine. No one really cares, but when you conjugate them, they become water soluble. Okay. Now, the whole point of bile is to help with digestion and absorptions of lipids. Okay. So the way that they do that is that they're just going to surround like a lipid molecule and help it pass through and get absorbed, okay, into the body. That's all that bile does. Okay. That's like one of the main reasons of bile. Okay. Now, it also helps with bilirubin and cholesterol excretion. It's the body's primary means of elimination of cholesterol and bilirubin is through the bile. Okay. That's the two main functions that I want you to know. It helps with digestion and absorption of lipids and fat-soluble vitamins, as well as bilirubin and cholesterol excretion. It's the primary means of elimination for bilirubin and cholesterol excretion. All right? Now, it's made up of a bunch of different things. We already discussed the bile salts, but another thing that it's made up of is cholesterol, bilirubin, as well as cholesterol 7-alpha hydroxylase, which helps catalyze the rate-limiting step of bile acid synthesis. Okay, that's something that they want you to know. So it's made up of all these different things, and to finally make it, the rate-limiting step of bile acid synthesis is cholesterol 7-alpha hydroxylase. And we'll talk about the importance of that later on in a pathology video. Okay, now what happens? Well, most lipid absorption occurs at the jejunum. So this is where you're going to absorb your lipids via the bile, right? And what happens is that majority of the bile is going to be recycled because it's going to get reabsorbed at the distal ileum, which we already discussed. So in patients that have pathologies that lead to decreased absorption of enteric bile salts at the distal ileum, like in patients that have like short bowel syndrome, or if they had a ileectomy, Crohn's disease, it can prevent normal fat absorption and it can cause bile acid diarrhea. So let's take a step back. Let's say, so remember, majority of your bile is going to be recycled. It's going to get reabsorbed after release from the gallbladder. It's going to get reabsorbed at the terminal ileum. Let's say there's some type of pathology. We won't focus on what pathology, but let's say there is one that's blocking the terminal ileum. Something's going on in the terminal ileum, and so bile acids cannot get reabsorbed. So that means you're essentially pooping out all of your bile acids. So what happens next time you eat, you have an overall decrease in the amount of bile that you have. So that means that you're unable to reabsorb the lipids and the fat-soluble vitamins that you normally once were able to. Okay, so you could potentially see like a vitamin A, D, E, K deficiency. This is all very key to understanding what's going on at the basic level. Okay, I want you to keep that problem solving in your mind. Okay, biles help with fat soluble vitamin absorption. If you have something going wrong with bile, it doesn't even have to be terminal ileum problems. It could be anything going on with bile. Then you could present with odd symptoms that they will give you like vitamin A deficiency symptoms or vitamin D deficiency symptoms. Okay, A, D, E, K. Okay, those are fat soluble vitamins. Now, another thing that you could see is calcium, which normally binds oxalate, is going to bind fat instead. So free oxalate is absorbed by the gut, and it's going to lead to increased frequency of calcium oxalate kidney stones. We already discussed that in the kidney stone chapter, but once again, this is a common pathology. So if you have an overall decrease in bile salts, what's going to happen is that calcium is going to bind fat instead of oxalate. And when calcium binds fat instead of oxalate, you have more free oxalate, which is absorbed. And so then that free oxalate is going to have to leave the body via the urine rather than the GI tract. And what happens is that it's going to bind calcium in the urine and it's going to cause kidney stones. All right. So there's a lot of pathologies associated with bile. I hope that makes sense. We already talked about that increase in frequency of calcium oxalate kidney stones in the renal chapter. So if you want to go back to it, you can discuss it. But just keep in mind what's going on with bile. Okay. And remember, it's helpful, two functions: digestion and absorption of lipids and fat-soluble vitamins, and two, it helps with bilirubin and cholesterol excretion, which is the primary means of elimination of the body. All right, so now we should talk about bilirubin. So before I talk about bilirubin, I want you guys to, I'm going to kind of just discuss this real quick. So in my mind, so bilirubin is made, essentially, there's one of the main factors that creates bilirubin is lysis of red blood cells. Okay, so what happens is that you have lysis of red blood cells and heme flows out into the plasma, okay? Because red blood cells contain heme, right? And heme contains, it's broken down, and it contains bilirubin, okay? So essentially when you have lysis of red blood cells, you get bilirubin within the blood, okay? And so what happens next is that the bilirubin needs to be broken down. So it gets sent over to the liver, okay? And the bilirubin gets sent over to the liver to be conjugated, all right? So it's currently unconjugated, all right? They call it unconjugated bilirubin. Then it gets sent over to the liver in order to be conjugated. All that means is in order for it to become water soluble, okay? And so the liver does things to it and it conjugates bilirubin. So then it's known as conjugated bilirubin. Okay, and unconjugated bilirubin is known as indirect bilirubin, and conjugated bilirubin after the liver has done its work on it is known as direct bilirubin. Okay? And then that direct bilirubin is going to be released, okay? It's going to the gallbladder to be stored as bile, and then the gallbladder will contract and it will function as normal bile. Okay? So this is why bilirubin and bile come together. So now let's take a step back. Let's think back to our hemonc chapter. Patients that have hemolytic anemia. They have hemolytic anemia, which leads to an increase. There's so much amount of lysis of red blood cells. So if there's so much amount of lysis of red blood cells, what happens? There's going to be so much amount of bilirubin, unconjugated bilirubin, in the blood flowing because you have an overriding of the system. And the liver is not able to keep up with conjugating this bilirubin, right? So what happens? Well, all that unconjugated bilirubin, it starts to build up within the body, within the blood. And so it's going to start to deposit all over the place. And so where does it deposit? It deposits in the skin. It deposits in the eyes. All right? And that's why patients become jaundiced. All right? And patients with hemolytic anemia, that's one of the reasons they become jaundiced, because there's such large levels of unconjugated bilirubin. Now, here's the final connection. Why do they look yellow when they're jaundiced? Well, take a step back. Have you ever vomited bile? Have you ever vomited on an empty stomach? I'm sure a lot of people have, because whenever you're sick, you definitely have tried to, if you're vomiting and you haven't been able to keep down food, you start to vomit bile because that's the only thing in your stomach. Take a look at what that bile looks like. It's green. It's yellow. So imagine that completely dispersed around your body. That's why your skin turns yellow. That's why you have scleral icterus. That's why you see yellow deposits within the eyes, within the skin, okay? So all of that comes together, and I hope that process is clear to you, okay? Because that made it so much clearer to me. All that it is just pretty much bile, okay? It's bilirubin, which is just a waste product of heme, okay? That's going to be conjugated later on to be formed into bile, all right? So it's essentially the same building blocks for bile, all right? So let's kind of take it back a step, and I'm going to walk you through, again, bilirubin, okay? So bilirubin, you're going to start as a red blood cell. Red blood cell, let's say it lyses and heme flows out. And remember, you're always going to have bilirubin. It's not some pathological issue. It's not always due to the fact that red blood cells are lysing pathologically. Remember, we always need to break down red blood cells. Red blood cells are being, killed every single day by macrophages and, produced again, right? The normal lifespan of a red blood cell is only around 90 days, I think, okay? I mean, don't quote me on that, but you're always constantly overturning your red blood cells. So this is not a pathological process all the time. This is physiologic. We will always have bilirubin in the body. Okay, so red blood cell, for no matter what reason, it's going to lyse, it's going to be killed off by a macrophage. And in the macrophage, it's going to produce heme, you're going to grab the heme, and the heme is going to turn into unconjugated indirect bilirubin. Okay, so unconjugated bilirubin is then going to travel to the liver. The liver is going to conjugate the bilirubin, okay, and make it direct bilirubin via UDP glucuronylysyl transferase, okay, UDP-GT. Got it? That's what helps unconjugated or indirect bilirubin become conjugated or direct bilirubin. Then it's going to flow out of the liver and into the gallbladder to stay and be stored. Okay? Gallbladder is going to contract in response to a lipid-high diet, and it's going to go out into the GI tract where it turns into urobilinogen. The urobilinogen, okay, is going to be excreted in the feces as stercobilin, and that's what gives the brown color in feces. Right? Because it's a yellowish, greenish color. It's going to give it a brown color when digested, okay? And then some urobilinogen is not going to turn into stercobilin. It's going to go to the kidneys, and it's going to be secreted as urobilin, and that's what gives the urine the yellow color. Okay, so I hope that all makes logical sense to you. Just think back to, I don't want to go through the whole process again because I think I'm belaboring the point, but this whole process is very easy to understand. Now, remember, the rest of it is going to be reabsorbed at the terminal ileum, back to the liver, back to the gallbladder to be stored again and used again.